Dear students, now let us discuss about the continuous functions on intervals. So, first let us discuss what about the boundedness of a function. So, suppose A is a subset of R, let A be a part of R. Now define a function f from A to R. Then f is said to be bounded on A. F is bounded on A if there exists an m, a real number m or a constant m which is greater than 0 such that f of x modulus of f of x less than or equals m for all x falling A. The function f is said to be bounded, a continuous function. The function f from A to 1 is said to be bounded on A, means its domain, when there exists a constant m that is positive greater than 0, m is sufficiently large, with a modulus of f of x less than or equals m for all x falling A. Then the function is said to be unbounded. If a function is not bounded, then it is unbounded. The condition for the unboundedness is modulus of f of x greater than m. Modulus of f of x greater than m for all x falling A, then the function f is said to be not bounded or unbounded. Agree. Now, what is the boundedness theorem? So, or consider a function before f of x equals 1 by x. Consider a function f of x equals 1 by x defined on interval a equals open interval 0 infinity. What about this function? Is it bounded? No. So, it is not bounded on a. Why? Because for every m positive, put a x equals or xm equals 1 by m plus 1. xm equals 1 by m plus 1. So this 1 by m plus 1 also falling there. A itself. Now, what is f of xm? So here f of xm equals 1 by xm. Agreed. f of xm equals 1 by xm. So what is 1 by xm? 1 by xm equals m plus 1. M plus 1 means which is greater than m. Okay. So the function is not bounded. So a function is not bounded or unbounded means modulus of f of x greater than m. It is said to be bounded when mod f of x less than or equals m, where m is a particular constant. Clear? Here consider the function f of x is 1 by x. Put xm equals 1 by m plus 1. xm fallen where? Again a itself. So what is f of xm? 1 by m plus 1 or 1 by xm, that is 1 by m plus 1 is m plus 1, that is greater than m. So by means of this argument, f of x is modulus of f of x greater than m. This means modulus of f of x greater than m. That means the function f is unbounded. Agreed. So this is the criteria or this is the condition for the boundedness and unboundedness of a function. Clear? Now let us discuss the boundedness theorem. Come to the theorem. Here the theorem states that, boundedness theorem states that I equals closed AB. Boundedness theorem states that, boundedness theorem. Boundedness theorem. Let I equals closed AB be a closed bounded interval. Let f from I to R, f from I to R, I is a subset of R. Let f from I to R be a continuous function on I, then is continuous on I, then f is bounded. Then f is bounded on I. That is, the continuous function on a closed and bounded interval is always bounded. That is the boundedness theorem states that the continuous function on a closed and bounded interval is always bounded. Here I equals closed AB be a closed and bounded interval. F is a continuous function on I. There is a from I to R be a continuous function on I. Then we have to show that F is bounded on I. How? So its proof is by contradiction method. First suppose that F is not bounded on I. F is not bounded on I. So F is not bounded on I means for all n fallen n, for all natural number n, for all n fallen n, there exists xn fallen I such that modulus of f of xn greater than n. Modulus of f of xn greater than n. Why? Because we assume that f is not bounded on I. So by the condition of unboundedness, for all n fallen n, there exists xn fallen I such that modulus of f of xn greater than n itself. Agreed? So, but what is xn? Xn fallen I. What is I? I equals closed interval AB. That means A less than or equals xn less than or equals b. Clear? Okay. A less than or equals xn less than or equals b means the secant xn is bounded. Sure? Okay. Secant xn is bounded. By Bolzano-Weierstrass theorem, the secant xn is bounded. Therefore, secant xn has a convergent subsequence. So let it be x dash. X dash equals xnr. Be a convergent subsequence of this x. Okay. Yes. Now let it limit x dash. Convergent subsequence. So it is convergent means its limit exists. So limit x dash equals limit xnr equals, suppose it is x star or x, whatever it may be. X, not x star, it is simply x. So limit x dash equals limit xnr equals x. Why? Because secant xnr be a convergent subsequence means its limit exists. Therefore limit x dash equals limit xnr, let it be x. Okay. But what is xnr? XNR is a subsequence of xn, but xn fallen where? AB. Therefore, A less than or equals xnr also less than or equals b. Okay. A less than or equals xnr less than or equals b. Why? Because xnr also fallen. Because secant xnr be a subsequence of secant xn, but secant xn fallen where? Xn fallen closed interval AB. Agreed. So take the limit means A less than or equals limit xnr also less than or equals b. Limit A means A. Take a limit on both sides. So A less than or equals limit xnr less than or equals b. But what is limit xnr? That is x. That means A less than or equals x less than or equals b. Okay. A less than or equals x less than or equals b means the limit x be the limit. So limit of fallen where? I. What is I? Closed interval AB. Okay. So A less than or equals x less than or equals b means x of fallen closed interval AB. But closed interval AB is I. So it is nothing but I means x of fallen I itself. Agreed. Now come to the speciality of f. What is f? What is f? F is continuous on I. Since f is continuous on I, so this f is continuous at every point of I means f is continuous at a particular point of I, let it be x. Okay. Our assumption is f is continuous on I, or the hypothesis is f is continuous on I. F is continuous on an interval means f is continuous at each and every point of that interval. So let x be any point on that interval, therefore f is continuous on that point x. F is continuous at x. That means since f is continuous or f is continuous on I implies f is continuous at x. F is continuous at x. Okay. So, what is sequence XNR? Sequence XNR be a subsequence of Xn. So, XNR converges to where? X. Since f is a continuous function, then f of XNR also converges to f of x. Okay, f of XNR converges to f of x. F of XNR converges to f of x means f of XNR be a convergent subsequence. Okay, f of XNR is convergent. Since f of XNR is convergent, we know that convergent sequence is bounded, therefore f of XNR is bounded. Sure? F of XNR is bounded. But what's our assumption? I will assume that f is not bounded. So a contradiction to the choice of unboundedness of this f. This contradiction is due to our wrong assumption. Therefore, f is bounded on I. So this is the boundedness theorem. Means the boundedness theorem states that if f is continuous on a closed and bounded interval, then the function is bounded on that interval. Again, f of xn is if f is closed and if is continuous on I is closed and bounded interval, then the continuous function defined on a closed and bounded interval is always bounded. Boundedness theorem is an important result. That is, the continuous function defined on a closed and bounded interval is bounded. So this is the proof. Clear? Means we just assume that f is not bounded on I, but by the definition of the unboundedness, mod f of xn greater than em. But what is xn? Xn is chosen from where? Closed interval AB. So xn ranges from A to B. But therefore xn sequence xn is bounded. But by also know Weierstrass theorem, xn has a convergent subsequence. Okay, xn has a convergent subsequence. Let it be sequence xnr be a convergent subsequence of xn. Now, therefore, limit xnr equals x means it has a limit. Why? Because of its convergence. So, a less than or equals limit xnr less than or equals b. Why? Because xnr fall in I. So, a less than or equals, after taking the limit, a less than or equals x less than or equals b means x fall in closed interval AB. That is nothing but I. So, f is continuous on I. F is continuous at xy, because if a function is continuous on an interval, then it is continuous at each and every point of that interval. So f is continuous at that point. So xn converges to x means, or xnr converges to x. So since f is continuous, f of xnr also converges to f of x. So f of xnr convergent, but convergent sequence is bounded. Therefore f of xnr is bounded. That's a contradiction to the choice of f. We assume that f is unbounded. This contradiction is due to our wrong assumption. Therefore, the function should be here f is bounded. That is, the continuous function defined on a closed and bounded interval is always bounded. Agree? Okay. Now let us consider some definitions. First one, absolute minimum and absolute maximum. So what is absolute minimum? So consider letter A. Suppose A is a subset of R. A is a subset of R. R means set of reals. Let A be a subset of R. and define f from A to R be a function, then the f has an absolute maximum on I. A. F has absolute maximum. F has an absolute maximum on A. When if there exists a point x star in A such that f of x star greater than or equals f of x, or f of x less than or equals f of x star for all x of all in E. Then x star is said to be the absolute maximum point for function f on E. The definition is important. A is a part of R and f is a function from A to R. Then the function f is said to has an absolute maximum on the given domain A if there exists a point x star for A such that f of x less than or equals f of x star or f of x star greater than or equals f of x for all x of all. Similarly, the function f has an absolute minimum. F has an absolute minimum on A if there exists x star, understand, x star for an A such that f of x star less than or equals f of x for all x of all. For all x of all. So this is the absolute minimum. Absolute minimum and absolute maximum. So f has an absolute minimum on A if x star fall in A with f of x star greater than or equals f of x, and absolute minimum means x star fall in A with f of x star less than or equals f of x for all x of all in E. Okay, thank you.